Hello friends, I am Amiranur Nizami and today we are going to see the laminated composite plates subjected to thermal loads. Okay. So I have received a lot of mails and they have asked regarding some reference paper to study the laminated composite plates subjected to thermal loads. So a lot of paper is there regarding this. So the first you can say the main started by Tugnikar for the exact solution. Okay. Tugnikar and Rao. So I think in 1994, if you will see the paper, so he has given the exact 3D elasticity solution, exact 3D elasticity solutions subjected to thermal loads, subjected to thermal loads, and just after that, you can say at the same year you can see the paper of Noor and Burton, 1994 itself. He has given the paper regarding the same exact 3D elastic solutions. And then Savio and Reddy, Jane Reddy, you can see 1 year later, 1995, they have given the same elasticity problem. And the best, you can see the easiest what we want is the Bhaskar and Vardhan paper, Bhaskar et al. Okay. So in 1996, he has given the exact elasticity solutions, okay, exact thermoelasticity solutions. Okay, so you can say the simplest case for the 3D, you can say what generally we want to compare our results. Okay, our results of two-dimensional theory, of 2D theory are mainly compared using this Bhaskar's paper. Okay, so it is the most simplest one you can say among these paper. Okay, and then you can say the Bhaskar's paper has been carried by Kant et al. Okay, Tarun Kant from IIT Bombay. So in 2007 or 8. Okay, so he has also formulated this paper Bhaskar et al. Using the semi-analytical approach. Okay. So what mainly this paper consider? So this Bhaskar paper, let us see. So why Bhaskar paper is mostly cited, Bhaskar et al. So you will see in 1996, he has given the results for first cylindrical bending for cross-ply laminate, which was the extension of Pagano's paper. Okay, Pagano has given in 1969 for mechanical load. Okay, mechanical transverse load, or sinusoidal load. Okay, transverse load. While this Bhaskar has given this subjected to thermal loading. And then he has given also, Bhaskar has given the cylindrical bending for symmetric angle-ply laminate. Okay, so he has also given, so this was the paper also given by Pagano in 1970. Okay, subjected to again thermal load, mechanical load by Pagano, and Bhaskar has given these results with the thermal load. So Bhaskar has given with thermal load. Okay, so and then the third examples of this paper Bhaskar has covered. The third example for cross-ply laminate, or you can say bidirectional laminated plates. laminated plates, okay, which was also the extension of the Pagano's paper of bi-directional rectangular laminates of 1970. He has given Pagano. So for the mechanical loading he has given, okay, but this Bhaskar has extended this with the thermal load, okay. So that's why Bhaskar paper is mostly cited, because it covers both the cylindrical bending paper as well as the you can say cross-ply bidirectional laminated plates, okay. So we can see, let us see, and then finally we will see the results of this. I have formulated this Bhaskar's paper. I formulated Bhaskar's paper. Okay, so we will see the results in Matlab. I have coded it in Matlab. So we will see the results of this Bhaskar paper at the end, inshallah. Okay. So now we will go to the paper. So first of all, we have named the Tugnikar and Rao paper. So this is the one 3-dimensional exact solution. Okay. So this paper you can see cited in 1994. Okay. So this was published in 1994, and it's not much clear, but you can see it's quite cumbersome. Here you can see the temperature distribution is also exactly solved here, the 3-dimensional solution. Okay. In each lamina it is solved. Okay. And then the results finally they have given after solving for each lamina. So you can see these results here. Okay. And the next paper, what you can see the Savio Reddy paper, 1995. Okay, this paper published in 1995. So you can see here 3-dimensional thermal analysis of laminated composite plates. Okay, so he has also solved exactly, and thermal loading he has applied for each lamina. Okay, heat conduction. So for the anti-symmetric angle-ply laminates, you can see here the results. Okay, so these are the results here. And next, what I have referred as Tarun Kant's paper. So you can also refer this paper, Tarun Kant's paper. So he has also given the extension of this is the Bhaskar's paper. Okay, with the semi-analytical approach. And what we are mainly interested at this time is the Bhaskar paper. So mostly when you ask about the reference paper or from where to compare your results, okay, so this is the paper Thermo-elastic Solutions for the orthotropic and anisotropic composite laminates by Bhaskar, Vardhan and Ali. Okay, so you can follow this most easily. So basically most of the cylindrical bending paper, okay, are cited from here. So you can see here this paper solutions within the framework, uncoupled, not coupled thermoelasticity, but linear uncoupled thermoelasticity are solved. So benchmark numerical results you can see. So this is the paper he has given, and he has applied the thermoelastic stress strain relations here. Okay. And then he has solved the 3 cases. So one the flexure infinite long. So this is the first problem. Okay. Boundary conditions. So now we will see the numerical examples here. Okay. So first examples he has given for the cylindrical bending, first numerical examples 090. Okay, for the cross-ply laminate, and then this is for the symmetric angle-ply laminates. Okay, and the third one is for the bidirectional square laminate. Okay, and then you can see some plot also. So you can see here the first one, the second one, this problem, and the third problem is for the bidirectional laminate. Okay, so and then finally he has given this. So this is the paper you can refer for the comparison of the results. Okay, so what we want, let us see. Just I will show the results. So this is for the cross-ply, and so let me show the results for this. First of all, for the cross-ply. Okay, so okay, let me take for the 3 layer, and A by H equals to 4, 0, 90, 0. Okay. Let us run this code. Okay, so this is the what we are getting. This is the transverse displacements. Okay, W, and the second one is in plane displacements, U, and the third one what we can see here, that is the V is 0 because it's a cross-ply laminate cylindrical bending case. Okay, and this we can see, so sigma xx in plane normal stress, and then it is in plane normal sigma yy, and then sigma zz. Okay, and this is the sigma xz. So I think here maybe the plot is also given in the paper. Let us just see the paper. Okay, let us just see the plot, last plot. I think one plot is given. Yeah, so this is the plot, figure 9, tau sz. Okay, or A by H equals to 4 and 20. So we can also see here our figure, Matlab figure. Yeah. So yeah, so this is this figure. If we see here tau sz, so that is the figure given here. Okay, the value. In the rest plot there is for the bidirectional laminates they have given, but this is the plot they have given for the cylindrical bending cases. Okay, so now how to compare the results, let us see. So whether we are getting the correct results or not, let us check. Yeah, so here I should make it some. Okay, maybe it would be somehow, I'll just underline here. So U at plus minus h by 2, 7.470. So you can see here the results. Okay, so U 7.4696, that is the 47. Okay, so the second digit he has taken, so up to 4.7. So you can see 7.47. Then V is not there because V is 0. Then W bar, that is the transfer displacements. So you can see here W is minus 18.32. So you can check here, W is 18.32, exactly matching. Okay, and now let us see for sigma xx. It is shown here. So at which place it is shown, plus minus h by 6. So this result is corresponding to what? Minus 0.15 means h by 2, then h by 3, then h by 4, then h by 6. So corresponding to h by 6, we have to see the results. So h by 6 here it is showing h by 6. So corresponding to h by 6, we have to see the results. And then tau xz is here corresponding to h by 6, and similarly sigma z is shown here for the h by 6 results. Okay. Sigma xy is 0, and then again sigma xz value you can see. Okay, and finally we are having sigma zz value. Okay. So this is the first case, and then the second case we will see for the infinite distance. So let us go back to the symmetric angle-ply laminate. So this is for the cylindrical bending. Let us see. Again we will run. So we are running A by H equals to 4, okay, and 30 minus 30, 30. Okay, for this lamina we are running this code. Okay, so now we are getting this results. So this is the results for the in plane displacement, transverse displacement W, U in plane displacement, and V. Okay, so we will check also the values for this, we are getting exactly or not. Hence the plot is not given here in this paper. You will see the paper, they have not shown the plot for the cylindrical bending cases, only the cross-ply cylindrical and cross-ply bi-directional plates they have given. Okay, V0, 90, 0, 0, 90, 0, but no cylindrical bending related results are here. Okay, so they have given only the tabular form. Okay, so that's why we have to go for the table to see the results. Okay, no issue. So this, and also you can see the shear stresses, and this is the stress also you can see. So this is the sigma xx, and this is sigma yy, sigma zz, tau xy, and then it is tau xz. Okay, and this is tau yz. So hence you can see the sigma zz is very different other than what we see in the mechanical loading. Okay, so this is very different way it is shown. Okay, so now come to the tabular results. So let us see. Okay, so u value. So u for this value is for A by H ratio 4 we are going to see. It is 10. Sorry, it is 104.3. So you can see it is 104.3. Okay, so it is plus minus h by 2. So you can see, okay, 1.403 on the plus h by 2. So basically these results are shown for the minus h by 2, minus thickness by 2, and plus thickness by 2 at the edge. Okay, top and bottom. So it is at the bottom, and this results is at the top. Okay, so 104.3, 104.3. So you can see here, so we are getting those results. Now V, what is the V value is plus minus 8.11.81. So V value is 11.806. So 11.81, or we are getting from here, or at this edge also we are getting 11.8. Okay. Now we will see W value. Here it is 79.62, and here also minus 79.62. So let's see the results. What we are getting. W 79.63. Okay, so 627. So if we will round off, it is 79.63. Okay, and then what we are having, sigma x at plus minus h by 2. So top and bottom. So 218. So you can see 218.6. Okay, and then it is sigma y 784. So sigma y at h by 2 plus 1 h by 2. So 784.7. Okay, and similarly you can see sigma xy and all results. So sigma tau xy, okay, 323 point this, so 323 point this you can see here. Okay, so it is 323.2, and then tau xz at plus minus h by 6 value. So you will see here by getting the h by 6 or thickness by 6 value. Okay, corresponding to this you have to see the value. So it is the port value, you can see 8.376. okay, so you can see here 8.37. okay, so this is the result. Similarly sigma yz and sigma zz, you can see the results here. Okay, so both tau yz and sigma zz you are getting same results. So this is the one which you can compare. Okay, so I think this results is you can say you can go through this paper, Bhaskar's paper, and that is the most you can say easy for us to compare, okay, the results from here for the cylindrical bending as well as for the cross-ply bidirectional laminates. They have given this. Okay. So if you want to go for the anti-symmetric cross-ply laminate, so you can go through the Tarun Kant sir paper, and he has given for the anti-symmetric also, I think, here by using the semi-analytical approach. It's near to the exact solution, very closely matching with the exact solution. I think he has given for the anti-symmetric cross-ply laminate also. Yeah, 090, 090. Okay, so if you have that, you can follow this paper also for that. Okay, so here we will close, and I think in the next class, if something what we will do, okay, we will see some more paper related with the thermoelastic, thermal loading, and okay, thank you.